Okay, guys, you ready for some sobering news? Chemistry, AP chemistry, last year, same as this year. Guys, this is it. We just got done with the unit over kinetic theory, gases, and solutions. We have 2 more units left in the year. That's it. 2 more units left in the year. You're saying, wait, I see 3. Guys, electrochemistry is 2 days, and typically what happens is you take home the test as like an open book assignment. So guys, literally, we have 2 more units left in this class. So let's give you the big overview, and then let's talk about the connector. So guys, this unit is really the last unit that we did in Gen Chem last year. We had this amazingly hurried last unit of the year where we talked about reaction rates, we talked about equilibria, we talked about Le Chatelier's principle, but we did all of that from a 30,000 foot view. That's why I encouraged you to KWL chapter 15, and I will similarly with 16. But guys, the other thing we did last year in the middle of that was acids and bases. But guys, we didn't tie any strong connectors between those things. So let me explain to you how the rest of the year is going to build but be different than last year. So guys, last year when we did reaction rate, it was just what makes reactions go faster and slower. Now what we're going to do is we are going to use reaction rate as an investigative tool. We're going to talk about things called reaction mechanisms. And so guys, the deal is this. When you look at a balanced chemical equation, it's really like a birth announcement and an autopsy. The reactants are where the reaction begins. Hey, I'm alive. The products are where the reaction ends up. Hey, I'm dead. But guys, what it doesn't tell is the life story. How do reactants turn into products? What are the changes? What are the mechanisms? What are the pathways that go on behind the scenes? So guys, what we're going to do in this unit is we're going to review what we know about reaction rates, and then we're going to tie what we see in terms of reaction rates about what that applies about what's going on behind the scenes. Those are called reaction mechanisms, which should be familiar from having reviewed chapter 15. Then guys chapter 14. Wait, did we do 14? Did I tell you guys the wrong chapter? Shoot. We're okay. Guys, I may have fucked you up. Wait a minute. We're still going to be fine because you've already talked about the beginning of this. Oh my gosh, guys. It was to have been 14 and 15. We're okay. Especially today because it's all going to be review. And eventually we would have needed to have done 15. We'll talk at the end. But continuing with our connecting thoughts here. Guys, then what we're going to do as we move out of reaction rates is we're going to tie it to equilibrium. This idea of reactions going both directions simultaneously. That's going to end up this unit. But then, guys, we're going to move forward from there, and we're going to talk about the idea that a lot of the systems that reach equilibrium are acid-base systems. And then, guys, frankly, in this next unit, we are going to talk about, first of all, really fascinating stuff, but also the stuff for the first time when I was a high school student, I couldn't figure out. Have I told you about my advanced chemistry experience in high school? I'll tell you more about it later. It was weird. But guys, when we got into buffers, my senior year in high school, couldn't figure it out. Like, it's the first time I ever remember in high school being stuck and not knowing what to do about it. Frankly, it's just made me really good at teaching it because I've had to think of ways to make hard accessible. But guys, when we get into chapter 16 and 17, we're going to be all about acid-base chemistry, equilibria systems, buffers, titrations. It's a very active and interesting unit. And then guys, after that, chapter 20 is 2 days and a test, and we're ready to start just doing AP practice problems in here. Then we'll eventually get done with all of our labs, and then third period also becomes just practice for the AP exam. So that's the big idea. It's coming fast. All right. So guys, with that said, you've got the class notes in front of you. A lot of this is review, as we said. So guys, I did not give you the title slide, but please, at some mental level, let these two terms enter into your brain. Guys, one of them is rate expressions. This is the only day we are going to do rate expressions. Then for the rest of this unit, we're going to do rate laws. And so guys, you need to understand there are rate expressions, rate laws. They're radically different from each other. And guys, today we're going to do rate expressions. So we're going to start with review. We're going to talk about some superficial ways of quantifying reaction rate. Then guys, we're going to talk about rate expressions, and that's going to be our day. So guys, looking at the next slide, I believe this is your first slide. Guys, you have all of this in front of you, right? So there's no sense in me hiding it from you because you've already got it. But guys, here's what I'd like you to do. So chemical kinetics is a study of the speed of chemical reactions or reaction rates, which we've already talked about. Then guys, these are the things, and it was cool because Michael was tying this into gas pressures in the last unit. I love making connections. But guys, when we talk about reaction rates, we know that there are 4 things, and this is still the exhaustive list. There are 4 things that affect the rate of a reaction: concentration, temperature, physical state, which last year we called surface area, and then catalyst. So guys, here's what I want you to do. With the person next to you, brain dump everything that you remember about reaction rates. What are the underlying factors that cause these things to affect rate? Why do these things affect rate the way that they do? And then guys, you've got the notes on catalysts, so you can talk about that too. So guys, at the very least, answer the whys. But if you dare go deeper, which I hope most of you can, what are the underlying principles that make all these things true? Guys, you got about 3 minutes. Dig in. And by the way, guys, take notes from each other. You want to be writing this down on paper. If you're really feeling brave, draw pictures. No, so physical state is surface area.
But doesn't mixing things up make the reaction go differently if you didn't mix it?
It can. We may as well just talk about it. It can, but it's really technically a function of surface area. Because if you've got 2 things, in order for them to react, they have to be exposed to each other. And if they always lie in this orientation, the unexposed faces aren't reacting. Where if you spin them, they're reorienting to each other, which functionally opens up surface area. The misconception that some people have is that temperature is a function of molecular motion, and so if you stir it, you're increasing the kinetic energy of the molecules, and that's not true. You can't stir, well, generally you can't stir something fast enough to make it hotter. Yeah. What's that? Unless you have a blend tech, and then, have you seen those videos, Will It Blend? Yeah. All right, guys. I'm going to offer you this. I would suggest to you that every thought, that every idea, that every answer that you wrote down or didn't write down on your paper can all be summarized in this. That's it. Everything that you need to understand about reaction rates and the things that affect it all come down to this graph. So guys, if you didn't draw this graph, probably worth drawing the graph. So guys, let's label our axes. This is what we call loosely reaction progress. You could think of it as time. This is energy. These are reactants. These are products. What's the hump? Do you remember? Activation energy. Guys, this hump right here is E sub A, which is the energy of activation, or we call it more commonly activation energy. Now, what does this have to do with stuff? Well, guys, what do reactions do? Fundamentally, they turn reactants into products. In order to do that, they got to get over the hump. So guys, fundamentally, in order for reactants to turn into products, they have to touch. We use the term collision. But guys, not all collisions are effective. In order for a collision to turn reactants into products, they have to reach this peak. We may as well talk about it now. Guys, this is what is called activated. This is what is called the activated complex. We'll talk more about that later, but this peak right here is what we call the activated complex. So guys, if a collision is successful in reaching the apex of that hump, turning into the activated complex, guys, at that point, and now we can use the term, it's spontaneous. It now rolls down the backside of that hill and reactants turn into products. But guys, what happens if a collision occurs and it doesn't make it to the top of the hump? It's as if nothing happened. They don't turn into products, and the more that happens, the slower the reaction goes. So, saying it in the positive, and guys, this is all about collisions. The more collisions that are effective getting over the hump, faster the reaction goes. So guys, what is it that makes collisions effective? One is the frequency of the collisions. That's how we talk about it. The more collisions per unit time, the faster the reaction can go. But it's also a question of magnitude. They can't hit often and not hard. So guys, they've got to hit with high frequency and or high magnitude in order to get more collisions over the hump. So now let's talk about this. Guys, concentration. If you increase the concentration of a solution, if you increase the concentration of the reactants, that makes the reaction go faster. Is that a frequency or a magnitude issue? Frequency. And guys, you can't just say that. You have to say frequency of collisions. But it's a frequency of collisions issue. Guys, what about temperature, frequency or magnitude? Both. They hit more often and they hit harder. Guys, physical state is surface area. Is surface area a frequency or magnitude issue? It's a frequency issue. Guys, like grinding something up in it makes them hit more often. Do you now understand why we're doing the lab third period? Go ahead. It can, but solid, liquid, and gas are also a function of surface area. So for example, if you I don't know, go to the beach, go camp, whatever. You load up a cooler with drinks, right? If you stop by the Sev to grab ice, you can either get cubed ice or block ice, right? So cubed ice has got a ton of surface area. And as a result, it cools things down really quickly, but it also melts like crazy. If you're going camping for a week, that's when you buy block ice, because the block ice has more surface area, or less surface area, so it melts less slowly. So then the question is, why don't we put liquid water in our coolers? And there we've got so much surface area that the heat it's also a phase change thing. But yeah, so definitely, so phase affects reaction rates. Well, you're going to do that kind of. Could we replicate that in this lab? Could we take an Alka-Seltzer tablet, grind it up, and that's really, I guess you could dissolve it, but that's sort of the reaction to begin with. So yes, phase does matter, but that's then a function of surface area relative to, yeah.
Would that not also affect magnitude because like gas particles are moving faster?
That's interesting, potentially, but then that's not a universal standard, right? Like frozen water and frozen carbon dioxide, same phases at different temperatures. You're right that their liquids would be warmer and their gases would be warmer, and therefore more reactive, but that still comes back to temperature. So the safe way to cover your bets is let temperature be temperature, and if those changes in temperature cause a change in phase, then you're right that you would have a collision issue with temperature and then also a collision issue with surface area if those phases present more surface area. You know what I'm saying? Yeah, it's interesting, Claire. I've never toyed with that in my head. And you're right, but I've never seen them bark up that tree. Okay. Then guys, finally this, what about catalysts? Is that a frequency or a magnitude issue? It's neither. Guys, and this means nothing to you, but it will. Guys, catalysts drop the hump. How do they do that? We can't talk about it because you don't understand reaction mechanisms. Guys, reaction mechanisms, again, are the behind-the-scenes story of how a reaction gets from reactant to product. And once you understand reaction mechanisms, then we can talk about what catalysts do, because catalysts magically cause reactions to go through different pathways that have different activation energies, typically lower. So we can't really talk about catalysts until we get deep into mechanisms. So guys, anything there you need to talk about? Y'all good? Okay. So guys, in general chemistry, we simply said faster and slower. In AP, we need to talk about how much faster and slower. And that leads us, my screen's going to freak out. Guys, that actually leads us to the idea of quantifying reaction rate. And so guys, the idea is this. When we quantify speed, we have change over a given unit of time. Your car is changing its position by 65 miles every hour. The engine inside your car is spinning at 6,000 revolutions per minute. By the way, that's what the other dial in your car is measuring that isn't speed. My daughter just put a sticky note over it because she doesn't even know what it means. But guys, you typically have a speedometer, how fast your car is moving, and a tachometer that tells you how fast your engine is spinning. And both of those things are change over time. Miles per hour, revolutions per minute. So guys, if that's the case, how do we measure the speed of reactions? Well, what do reactions do? Well, reactions make reactants turn into products. So how do we measure amounts of reactants in products? Moles. How do we measure time? Minutes. What are our units for reaction rate? For now, they are moles per minute. Now, guys, this brings us to a very important point. Turning the page. Guys, you'll notice that I stole the data from you. This is new and different. But guys, we could spend days picking this apart. We're not going to do it now, but we're going to establish some important principles. Guys, please don't go passive because you have the notes in front of you. Your understanding of these important ideas is going to determine your success as we move forward. So guys, it goes like this. Imagine that we have a hypothetical process where A turns into B. That's it. Simple hypothetical. So guys, it looks like this. We're going to do this in mason jars. And I love that the images are in mason jars because it drives home the point that this is hypothetical. But guys, here's the idea. If we collect data on this relative to time. So guys, at time 0, you'll notice the little hypothetical clock. So guys, at time 0, here's the idea. At time 0, we're going to say that all those red dots represents 1 mole. Then guys, how many blue dots are in that first cylinder, that first mason jar? None. So we have 1 and none. But now guys, this. After 20 minutes, we now, and do you have the 20 minutes in your notes? Did I not give you notes?
I didn't realize I was late.
Oh, shoot. Sorry. Just ask. Sorry. There you go. Okay. So do you have the times?
Yeah.
Okay. So guys, after 20 minutes, this. We still have some red left, yes? The amount of red that we have left, please write down, is 0.54 moles. Again, we're making up numbers. So guys, based on that, now how much blue do we have? How much B do we have? 0.46. We can do math, right? If all this reaction does is turns A into B, if we have 0.54 moles of A left, the rest of it turned into B. Makes sense, right? Now guys, watch this. 20 minutes later, we lost 0.46 moles of A in 20 minutes. So 20 minutes later, we'll obviously lose another 0.46 moles of A, and that will leave us with 0.08 moles of A, right? No, it's actually just down to 0.30. Now guys, I know that this seems stupid, but the math behind it is real. And importantly, the logic behind it is critical. Let's do the math. How much of B is left? 0.7 moles. I'm sorry, how much of B was created? 0.7 moles. So guys, here's the question. In the first 20-minute period, we lost 0.46 moles of A, turned into B. In the second 20-minute period, we lost 0.24 moles of A, turned into B. What's happening to the reaction? Slowing down. Guys, this is worth writing down. All reactions are always slowing down. All reactions are always slowing down. They are strong words. We'll talk about the qualifiers in a minute. But guys, all reactions are always slowing down. Talk with the person next to you about why. You already know the answer. Talk to the person next to you. Why are they slowing down? I think you guys got it. So guys, let's talk about it. Rather than talk about the words, let's look at the pictures. What was your measurement for things? Pant load? Butt ton? Crap ton. Okay. So guys, how much A do we have in jar 1? Crap ton. A lot. and they run into each other a lot, and the reaction happens a lot. But then, guys, when we get over here to B, example B, how much red do we have? A plant. I was going to say less than a crap ton, but a pant load, which is less than a crap ton. And so, guys, because we have less red, the reaction slows down. Why?
Because there is less red to react.
But how good. I love how you said that. There's less red to react with, and it gets even worse because we still have collisions, and now the blue is in the way, and every time red runs into blue, it doesn't run into red. So some of these collisions aren't even the collisions we're looking for in the first place. Just a second. Now, guys, this is an example of which of the factors that influence rate. Concentration. So, guys, the idea is this. As a reaction goes on, by definition, the concentration of the reactants is going down. And as a result, the reaction slows down. So, guys, that's worth writing down if you don't see that in your brain. Guys, this is a function of concentration. As the concentration goes down, the rate goes down, and that's what reactions do by definition, is gobble up reactant and turn it into product. Go ahead.
You're going to love this.
No, I'm not.
It's like a half-life.
I actually do love this because that's exactly where we're going with this. Yeah, right? And so what you're going to find is, last year, remember when we talked about half-life, it was, this is a half, and this is a half of a half. And we're actually, it's interesting. Guys, did you hear what Michael said, that this is a half-life? Here's the thing that's interesting. It's not always a half-life because it's not always this simple. If A is just turning into B, it's the same math behind half-life. But sometimes it takes two A's to turn into B. And then it's a different equation. And so we're going to talk about something called molecularity. And so what's going to happen is, and this is the way they treat it on the AP test, they show you the mathematical equations. They're on the equation sheet. But the thing that they really want you to do is be able to look at a graph that graphs concentration over time and go, that reaction is unimolecular, bimolecular, termolecular, based upon the shape of the graph. Does that? So, guys, the bottom line is, because you need to understand this, we are going to talk about half-life, and we are going to talk about the graphical representations. But, guys, we're not going to do it during this unit. Please hear this. We are not going to have these conversations during this unit because, frankly, it's just stuff you have to memorize and you're going to forget. So what we're going to do is we're actually going to do it during review after spring break, and we're going to look at it then, because then it's more fresh in your mind for the AP test, because frankly they just ask you to memorize the shapes of graphs and what that means. So we're not going to do it in here because it's just memorization. We're going to do it later. Yeah, but it is half-lives. So guys, reactions are always slowing down, right? Do you see where this is represented in this graph? Where, and guys, let's make sure, reaction progress time, number of moles. Red, well, we should ask. Guys, if you hadn't seen the mason jars, how do you know that red is the reactant? It starts with some. How do you know that blue is the product? It starts with none. But then, guys, if both of them start with some, then you're exactly right. And I heard Claire and Lindsay say it first. Guys, the reactant is the thing that's being consumed, and the product is the thing that's being created over time. So, guys, you ready for another half-life thought? Actually, no. We'll do the half-life thought in a minute. Guys, where in this... So, up and down tell us reactant and product. Guys, where in these graphs do we see slowing down? the slope. Guys, I know that for some of you, math is not your native tongue. I know that for some of you, never mind. It's slope. So guys, if you don't understand this for whatever reason, that's fine. But guys, slope, M, is rise, change in Y over X. So it's rise over run. Change in Y over change in X. So guys, our rise is moles and our run is minutes. Some of you may know this as the first derivative. But guys, whether you know that or not, the idea here is that the slope of a line tells you the rate of its change. So guys, down here, we have a really steep slope. A is going away like crazy. B is getting created like crazy. But guys, down here, our slope is decreasing. There's less rise over any unit run. So as that slope starts to level off, that's indicative of the reaction slowing down. So guys, again, I know you're coming at this from many different math backgrounds. You've got to know that. If you need to put it in your notes, do. Because guys, this is going to be critical for the rest of the year. Slope tells us rate. Is that okay? So then guys, this. What's the end game? Where do these things end up if we could push this graph all the way to the wall? They're asymptotes, not equilibrium. This isn't going both directions. Guys, this and this is an asymptote. Remember how when we talked about radioactivity last year, we talked about the idea that you never lose all the atoms? Guys, the same thing is true here. We talk about reactions going to completion when you run out of limiting reactant and the reaction stops. Technically, that's not really a thing. It stops enough that we call it stopped. But guys, there's always a little bit of reactant still lingering. It's so low concentration that it never runs into another reactant particle. But guys, understand these are asymptotes. This never goes to none, and this never goes to all. So now, guys, we got to talk about Elizabeth's concern. When I said all reactions all slow down, I like the way she said it. Those are strong words, and they are. But guys, this is the... Can I use the word caveat? This is the stipulation. You're not doing anything to the reaction to force it. You're not pumping more reactant into the reaction. You're not heating or cooling it in an effort to make it go faster or slower. So guys, when we say all reactions are slowing down, it means left to their own devices, and you're not artificially manipulating them in order to get them to go. If you're interested in the idea of artificially manipulating chemical reactions, you want to become a chemical engineer. That's seriously the job description of a chemical engineer, is to manipulate reactions so they do the things you want them to do. And then you get hired by a company that spends money to buy the reactants, and then you as a chemical engineer figure out how to manipulate that reaction so it makes a lot of product, and then they sell the product at a profit, and you get rich along the way because the company appreciates your ability to make the reaction work better. Guys, that's all chemical engineers do. That's their job description in a nutshell. So, guys, are we okay with all of these ideas? You good? Okay. Yeah, go.
At this point, I'm curious.
Yeah?
Does that mean that when you're like eating tables up, there's a very small concentration of like your right? It's like the reaction, there's always like a little bit left.
See, I would say there's a lot, because if you're eating salt, so you know this, you've never tasted salt,
Yeah.
right? It's dissolving into your... So I would say there's a lot of pure sodium and pure chlorine ions, which makes me understand I don't understand what you're saying.
Oh, I guess when you're, well, I guess not the ions.
Oh. So you're saying, could there be some sodiums and chlorines that actually are not elemental, or that are element? Yeah, the chlorine leaves as a gas, and the sodium ions, frankly, are just looking for somebody to give their electron to. So, and their concentrations are low enough that, but absolutely. And even when you dissolve salt in water, just by the law of averages and entropy, there are some of those chlorine ions that will, in fact, rejoin another chlorine ion, and they're released as chlorine gas. Yeah, absolutely. Not much, but yeah. Okay. You guys good on all of this? Yeah.
So all reactions slow down, but do you have a space of time where a reaction starts speeding up because it has super high, it's super endothermic or something?
But again, those are outside influences, right? So you in order for that to be the case, if something is endothermic, it's the environment that is pushing that reaction in the first place.
If the reaction had had a lot of entropy, so the entropy
Enthalpy
balance out, so it is spontaneous, but it's just super endothermic and there's a lot of entropy.
Yeah, so the underlying premise is that these reactions are spontaneous without outside intervention. So I understand what you're getting at, and it's an interesting hypothetical. And I'm sure there are cases where that is the case. The one that you see, and this is actually, I did my honors, so I was a part of the honors college at my university as an undergrad. And so in order to graduate honors, you had to do a thesis as an undergrad. And my thesis was actually about what are called BZ reactions. They are actually reactions that are in equilibrium. So they're cycling literally, and it's not these are equal. It goes this way and then the other way. So they are equilibrium systems, but they have a predominant direction at any given moment. So these are reactions that are cycling, and many times they change colors. So you'll be looking at it and you're like, oh, it's blue. Oh, it's red. Oh, it's blue. And it's changing colors based upon whether you have more reactant and product. But the thing that's interesting is the entire reaction is slowing down because the net movement of the whole system is moving towards slowing down, and eventually it stops. So when I wrote my thesis, my analogy was it's kind of like an airline stewardess walking up and down the aisles of an airplane. If she's going this way, she's moving forward. If she's going this way, she's moving backward, but the plane's still going that way. And that's a lot of times what happens is you have reactions that are slowing down even though their equilibrium are moving against it. Not your question, but it's something that you'll see more than your question. Yeah? Yeah, I understand what you're saying, but the answer is no, because technically the reason it's spreading is you're adding more reactant. You're introducing more wood. Yeah, so in that case it does speed up, but it's simply because you're adding more wood. You guys good? Okay, so guys, let's do this really quickly. This is not earth-shattering, but guys, you need to understand this idea then that so we talked about this idea of rise over run, right? Change in Y, change in X. Guys, that comes together like this. That when we talk about reaction rates, what we're talking about is typically change in concentration of products. We tend to track products rather than reactants, and then we do this relative to change in time. But guys, you already know that change is final minus initial. So when we do this sort of stuff, it's change in B, or it's the amount of B final minus the amount of B initial, and then that's divided by the time interval that went by. Again, final minus initial. Is that okay? You guys good with that idea? Final minus initial? Okay. So guys, here's the deal. This is not how we talk about reaction rate. This doesn't work. Up until now, we've said that we measure a reaction rate in moles per minute, and I'm lying to you. The premise and the theories work, but guys, moles per minute is stupid for two reasons. Why is the denominator stupid? How many chemical reactions have you seen in lab that happened on the order of minutes? Yeah, right? Guys, these things happen unless you screwed up your lab. Some of you have turned them into hours. But, guys, a minute is an eternity for a chemical reaction. So instead of minutes, we do seconds. But then, guys, moles is also a stupid way to measure reaction rate. Guys, what is a mole? It's an amount of stuff. So guys, if we go back to our mason jars, this is easy. We can count, typically by weighing how much stuff we start with. But guys, how on earth do you do beaker B? You can't. You would literally have to go, okay, reaction, you need to stop so that I can count how many of each of you got. And oh, by the way, all the A's over here and all the B's over there. And then I'm going to weigh the A's, and then I'm going to weigh the B's, and then I'm going to put you back together, and then you guys can keep reacting. Guys, this is data that you can't collect. It's impossible. But we still need to know amounts. So guys, if we don't do moles, and I know you've already cheated and looked at your notes. If we don't do moles, what do we do? Molarity. Why is molarity better? And guys, the answer is because we can measure molarity. Remember, it's concentration, right? But guys, molarity is better because we can measure it instantaneously without disrupting the reaction. How do we do it? You guys know the answers. You've done it in lab. Good. You can do it from pH. pH is the molarity of hydrogen ion. And so guys, if you're doing an acid-base reaction, we like to call this the entire next unit. Guys, you're going to stick pH meters in your solutions, and you're going to figure out their rates by watching the concentration of hydrogen ion change. That's one. What is another way that we can measure concentration without mucking with the reaction? You guys did this in lab. Yeah. Shine a light through it. Beer's law, right? This is what we're going to do. Well, you'll see. This is maybe what we're going to do. I haven't decided which rate lab we're going to do. But guys, you can shine a light through it. And by calibrating your colorimeter, you can figure out the concentration by knowing the absorbance and transmittance. So guys, the bottom line is this. When we talk about reaction rates, what we actually do is this. Our units are molarity change per second. Those are actually the units that we use for reaction rates. Molarities per second. So now guys, let me show you what the data actually will look like. So guys, consider this reaction. This is the reaction of butyl chloride reacting with water. How on earth are you supposed to know what butyl chloride is? It's not water. So guys, and you got to get used to this. They are going to throw chemical compound names at you on the AP test, and you're going to be like, I have absolutely no idea what that is. You're not supposed to. It's process of elimination. If this is water, this has got to be butyl chloride. But then guys, as this reaction goes on, we track the concentration of C4H9Cl. We know that's not hydrochloric acid, but we're going to track this. So guys, we're going to find out this is an alcohol, this is but how do we know this is an alcohol? OH. And so guys, the data looks like this. So guys, drink this in. Time is going on. This is different. We're in this and we can do reactants. Normally we do products. This is reactants. But guys, that's butyl chloride. What is happening to the concentration? And you guys know brackets mean molarity, right? What's happening to the concentration of the butyl chloride over time? It's going down. We're consuming butyl chloride. But guys, what is happening to the rate at which the amount of butyl chloride is going down? It is going down. This reaction is slowing down. Again, for those of you that are doing calculus, that's the first derivative. So, guys, how do we do this? Well, these things over here are the rate. So it's the change in amount, the change in molarity divided by the change in time. So guys, this column right here shows us the rate at each 50-second interval. So here, this reaction is consuming 1.9 times 10 to the negative fourth molarity of butyl chloride per second. But it's getting smaller and smaller and smaller and smaller and smaller. So guys, two things are happening. The amount of butyl chloride is going down. It's a reactant. But the rate at which the amount of butyl chloride is going down is also going down, indicating that the reaction is slowing down because the concentration is going down. That all sit with you okay? Is that all right? Okay. So guys, we've got one more thing to do and we're done. This is rate expressions. Guys, I stole some of the notes from you, so be ready. We may bleed 2 minutes into third period, but we're fine. So guys, when we talk about rate expressions, here's the deal. In the two examples that we talked about, A turning into B and butyl chloride turning into butyl alcohol, you didn't know the name. Guys, these were 1-to-1. One red turns into one blue. One butyl chloride turns into one butanol. Guys, it's 1-to-1. But guys, the question is this, what if it ain't 1-to-1? Then, guys, we have to write what are called rate expressions based upon stoichiometric relationships. So, guys, join me. A turns into two B's. So, guys, let me show you what this looks like. Let me give this to you visually. We're still going to have red be A, and we're going to have blue, right? I'm sorry, blue will be A, red will be B. This is molarity relative to each other. So guys, here's the deal. When one A breaks apart, it turns into two B's. So guys, if we lose one A, we will gain two B's. If we lose another A, we will gain two more B's. If we lose another A, we're going to gain two more B's. Does that relationship make sense? But here's the deal, guys. When we write rate expressions, we need to make these equal. This, the rate at which we're losing them, needs to be equal to the rate at which we're gaining them. So guys, what do we have to do to make the blue column look like the red column? We got to do two things. One, divide to make this shorter. And two, flip one of them over. And guys, how do we flip something over mathematically? Make it negative. So guys, this is what we do. When we set these equal, because they have to be equal, the first thing that we do is we make the change in reactant negative. You want to write that down. I think it's even there as a tick mark. Guys, we make the rate of consumption of the reactant negative. So what does that do? Guys, that flips it over. So now they're both headed in the same direction. But now we got to make them the same height. So what we do is we divide, in this case by 2, and that makes them the same height. But guys, where did the 2 come from? The stoichiometry. Does that make sense? So guys, when we write rate expressions, they have to be equal. To make them equal, we make the rate of consumption of the reactant negative, and we divide by the coefficients to make them the same height. Yes? So guys, let's do that with this reaction. Don't you have this, right? No? Don't write it down, just watch. So guys, this is how we write rate expressions. We already know that rate is equal to the change in the amount of A divided by time. But guys, we need to make that equal to the change in amount of B over time. So what do? Well, first of all, we understand that we got to flip this over. So we make the rate of change for the reactant negative. And then, guys, we divide by the coefficient to make them the same height. Guys, if you're scrambling to write this down, let's do one together, and then we're going to call it a day. So guys, if you're scrambling to write this down, just trust me, don't. We're going to apply it now. So guys, here's 2HI decomposes into an H2 and an I2. Guys, let's write the rate law. So we are going to start with the reactants. And this is how we represent it. We have one reactant, which is HI. So it will be change in concentration of HI divided by time. That is rate. Change in molarity over change in time. But guys, notice what we do. We make this negative because we understand that reactants are being consumed. And then we divide by 2 because that's the coefficient from the balanced equation. So now guys, you do the other two parts of the rate expression. So guys, this equals, we got 3 minutes left and then we'll take a full break. Eleanor, do you need more time on Friday? Perfect. Thank you for doing that. So guys, are you there? So how do we represent H2? The change in molarity of H2 divided by time. How do we do I2? The change in molarity of I2 divided by time. Notice that these are products, so they're already moving in the right direction, so we don't make them negative. And then we're not dividing by coefficients because they're ones. These are now truly equal. The negative of 1/2 the rate of consumption of HI is equal to the rate of production of I2 and the rate of production of H2. Thoughts on that? Yeah. So the amount of reactant is going down. So we make it negative to change the direction. These are already going up because they're being produced. And in order for them to be equal, they have to all be headed in the same direction. So to do that, we just make the reactants negative. We could make the products negative and make them all go in the downward direction. But the convention is make the reactants negative. You guys good? So here's the question. What are we going to do with this? This is what you're going to see in the homework and on the AP test. If H2 is being created at a rate of 1 molarity per second, what is the rate of disappearance of HI? So guys, what I'd like to do is I'd like to solve this with you, and then we're going to take a break. So guys, would you allow me to sort of steer the ship for a minute? So notice what we've got. We are talking about H2. I'm going to switch to a brighter color. Guys, we're talking about H2 and we are talking about HI. So what about I2? We don't need it. It's not a part of the question. So then, guys, the question becomes this. What do we know and what are we solving for? Well, guys, hey guys. It'll be just a second. So guys, we know the rate of creation of HI, or I'm sorry, of H2. So guys, all of this we are going to replace with 1 molarity per second. Getting really sloppy with significant digits. You know, guys, I want to move my equal sign. Maybe here. That might be more sensical. So now, guys, we need an x. So what are we solving for? We are solving for the rate of disappearance of HI. But guys, remember, rate is molarity divided by time. So it is change in molarity divided by time. So that is our x. So guys, it goes like this. Keep the negative, replace molarity divided by time with x, and then keep the 2. Now we can solve this for x. X is already in the numerator. So guys, in order to solve this, we cross multiply and we get negative x is equal to 2 molarity per second. But then guys, solving for x, we say x is equal to negative 2 molarity per second. So guys, let's talk about it mathematically, and then let's talk about it logically. So guys, what does the negative mean? Disappearing. So guys, we already have the term disappearing written into the question. So in order to answer the question, the answer would be the rate of disappearance is 2 molarity per second. If they had asked you what is the change without giving you disappear, which implies direction, then you would have to say the rate of change for HI is 2 molarity per second negative. Negative 2 molarity per second to indicate it's going down. So in some point, you got to give direction. If it's in the question, then you don't have to include the negative. But if it's simply asking about change, then you need to include it. But then, guys, this. Does it make sense? If we know that this is being created at 1 molarity per second, if this is being created at 1 molarity per second, doesn't it make sense that this is disappearing at 2 molarity per second? Because it takes 2 of these to make 1 of those. Guys, understand in this simple example, the logic makes sense because you can see it clearly. You're going to see that they're going to throw weird stuff at you. So remember this structure, and that'll serve you well. With that said, we're not going to do, after your homework tonight, we're not going to talk about these anymore until you take the test. So understand these are rate expressions. You're going to practice on them tonight. Rate laws, which is what we're going to start doing next time, is what the rest of this unit is all about. And we'll do that coming up. So, guys, you have the homework in front of you. Questions on any of this? You're geniuses. Guys, take a 5-minute break, come back, and we're going to bounce immediately into lab.